Hey everyone, welcome to my video. Have you ever wondered how something changes when there are multiple factors involved? For example, imagine the temperature in the room. It depends on both the location and the time. If we only change one factor while keeping the other fixed, how can we measure the effect? That's exactly what partial derivative helps us do. In today's video, I'll explain what partial derivatives are and how to calculate them, and why they are so useful in engineering and science. So what exactly is partial derivatives? Partial derivative tells us how a function changes with respect to one variable while keeping all the other variables constant, and also means that it measures change in one direction of a multivariable function. Think of it like adjusting only one control on the machine while leaving the others untouched. For a function that depends on x and y, the notation del f over del x means we are looking at how the function changes when x changes and y stays fixed. Similarly, del f over del y shows how the function changes when y changes while x remains a constant. Now you might be wondering how partial derivatives differ from the derivatives you've already learned. Ordinary derivatives deal with functions that have only one independent variable. For example, y equals f of x. Partial derivatives are used when a function has two or more variables. So instead of finding the slope of a curve, we are finding the rate of change in a specific direction. You can think of it as exploring different paths on a surface rather than moving along a single line. Alright. Now let's look at our first example. Here we have fxy equals to 3x squared y plus 2xy cubed minus 5y. And we have to find fx and fy. So over here, I've already done the calculations. Now, in order to find fx, we have to write down del over del x. This isn't d over dx, it's del over del x. So then you write down the equation. And now in order to find fx, you have to treat y as the constant and drag everything that isn't x out. So you have to drag 3y out, to drag 2y cubed out, and 5y. After doing so, we are left with x squared, x and 1. Differentiate the bracket, so differentiate x squared, we get 2x. Differentiate x, we get 1. Differentiate 1, we get 0. And times everything together, we're left with 6xy plus 2y cubed. Next, find fy. Same thing, del over del y. Then equation. Then when we find fy, we treat x as the constant and drag everything that isn't y out of the bracket. So 3x squared, 2x, and negative 5. Or 5, whatever. So now we're left with y cubed, and y. And then we differentiate the bracket. So we're left with 1. Differentiate y cubed, we're left with 3y squared. And differentiate y, we get 1 again. So if you don't know how to differentiate, you drag the number, the power, you times with to the front, and the power minus 1. So that's how you get 3y squared and also 2x over here. Then times everything together, you're left with 3x squared plus 6y squared minus 5. Right, now let's look at a slightly more advanced example involving exponential and trigonometric functions. Okay, the question we have here is gxt, function gxt equals to exponential power 2x sine t plus xt squared, and we have to find gx and gt. Alright, so first we have to find gx. In order to find gx, we have to treat t as a constant. So you have to drag out, same thing, drag out the t. Anything that involves t, we'll drag it out. So sine t and t squared. Then that leaves us with exponential 2x and as well as x. And now we have to differentiate exponential 2x and also x. So after differentiating exponential 2x, we get 2 exponential 2x because the value times down, the number 2 times down, and the power stays the same. And we have so after differentiating x, we get 1. So the 1 we times into t squared will still be t squared. So the final answer will be 2 exponential 2x sine t plus t squared. Alright, next we have to find gt. To find gt, we have to bring out the x, treat x as the constant and drag out all the x. So exponential 2x and x. So after dragging them out, we're left with sine t and also t squared. We have to differentiate these two. So after differentiating, after looking at the formula sheet, the table here, differentiating sine x, which is sine t, we're left with cos x. So in this case, we're left with cos t. Then differentiating t squared, we get 2t. Then we times it into the x, so we get 2xt, and we times exponential 2x with cos t, we'll get exponential 2x and cos t. Alright, so the next question we have is we also can find small changes in a function by using partial derivatives. So hxy equals to x squared plus xy plus y squared. When x equals to 1 and y equals to 2, we can find changes in h. So in order to start finding the changes in h, we have to first solve for hx and hy. So first we have to bring out everything that is y. So y squared, then we're left with x squared, x and 1. Then differentiate them, we get 2x, because we just bring down, we get 2x. Then differentiate x, we get 1. Differentiate 1, we get 0. Then times everything, times it in, everything times in, and we are left with 2x plus y. And for hy, we treat x as the constant, so we have to drag all the x out. So x squared, x, and there's no x here, so we leave it. And we are left with 1, then y, and y squared. And differentiate the bracket, we get 0, and 1, and 2y. And then times everything together, and we get x plus 2y. Then now we sub in x equals to 1 and y equals to 2 into hx and hy. So for hx, we get 4, and for hy, we get 5. Well, now that we talked about the examples, let's talk about why should engineers care about partial derivatives. One major application is heat transfer. Imagine a metal plate where the temperature changes depending on its position. Partial derivatives helps us determine how the temperature changes in different directions. Using these derivatives, engineers can calculate the temperature gradient, which points towards the direction of the fastest temperature increase. This concept is extremely important in thermal systems, fluid mechanics, structural analysis, and many other engineering fields. Well, to wrap things up, partial derivatives allows us to analyze how multivariable functions change one variable at a time. Now that we've learned what they are, how to calculate them, and how they apply in real engineering problems, I hope this video helped make the topic easier to understand. Thank you for watching, and feel free to ask any questions in the comment section below.
What's up? Because it's time to go beast mode.